sklearn, Neighbors. Description. The sklearn, Neighbors module in scikit-learn provides a variety of algorithms for implementing nearest neighbor methods, which are non-parametric, instance-based learning algorithms. These algorithms are particularly well suited for tasks like classification and regression, where the decision boundary is complex and might not be easily captured by linear models. Inputs. Training data: a set of data points, features and corresponding labels used to train the model. Test data: new data points, features that the model will use to predict labels or values. Outputs. Predictions: the predicted labels or values for the test data based on the nearest neighbors. Probabilities for classification: the probability of each class for the test data derived from the neighbors. Steps. Training. During training, the algorithm stores the entire training dataset. Prediction: for each test data point, the algorithm finds the k nearest neighbors based on a distance metric from the training data. Classification: k nearest neighbors. The predicted label is the most frequent class among the k nearest neighbors. Regression: k nearest neighbors. The predicted value is the average of the target values of the k nearest neighbors. Metrics. Accuracy: the proportion of correctly classified instances in a classification task. Precision: the proportion of true positives among the predicted positives. Recall: the proportion of true positives among the actual positives. F1 score: the harmonic mean of precision and recall. Mean squared error (MSE), a measure of the average squared difference between predicted and actual values in a regression task. Visualization plots. Decision boundaries. Visualizing the decision boundaries for classification tasks can help understand how the model separates different classes. Nearest neighbor distances. Plotting the distances of nearest neighbors can provide insights into the model's performance and identify potential outliers. Fine-tune parameters. N neighbors: the number of neighbors to consider for prediction. Weights: the weight function to use for the neighbors. Options include uniform: all neighbors have equal weights, and distance: closer neighbors have more influence. Algorithm: the algorithm used to compute the nearest neighbors. Options include brute force for small datasets and KD tree or ball tree for larger datasets. Metric: the distance metric used to calculate distances between data points. Common options include Euclidean distance, Manhattan distance, and cosine similarity. Uncertainty methods. Confidence scores. Confidence scores can be derived from the distances to the nearest neighbors, providing a measure of the model's certainty in its predictions. Voting ensemble: combining multiple models with different parameters can provide more robust predictions and improve uncertainty estimation. Challenges and fixes. Challenge 1: curse of dimensionality in high-dimensional datasets. The distance between all points tends to become similar, making the nearest neighbor algorithm less effective. Sample use case that resulted in challenge 1: a dataset with 100 features and 1000 instances, where the accuracy of KNN decreases significantly compared to a dataset with 10 features and 1000 instances. Fixes to challenge 1. Feature selection: reduce the number of features by selecting the most relevant ones. Dimensionality reduction: use techniques like principal component analysis (PCA) or t-SNE to project the data into a lower dimensional space. Challenge 2: sensitivity to outliers. Outliers in the training data can significantly influence the nearest neighbor search and affect predictions. Sample use case that resulted in challenge 2: a dataset containing a single outlier point with a very different feature value, leading to misclassification of other points that are close to it in other dimensions. Fixes to challenge 2. Outlier detection and removal. Identify and remove outlier points from the training dataset. Robust distance metrics. Use distance metrics that are less sensitive to outliers, such as Manhattan distance or Mahalanobis distance. Challenge 3. Computational complexity. Finding the k nearest neighbors can be computationally expensive for large datasets, especially with brute force algorithms. Sample use case that resulted in Challenge 3. Training a KNN model on a dataset with 1 million instances and 50 features takes an excessively long time. Fixes to Challenge 3. Approximate nearest neighbor search. Use approximate nearest neighbor search algorithms like KD trees or ball trees to speed up the search process. Data subsampling. Train the model on a smaller subset of the training data to reduce computational complexity. Challenge 4. Overfitting. The KNN algorithm can overfit to the training data if the number of neighbors is too small or if the data is highly noisy. Sample use case that resulted in Challenge 4. A KNN model with K1, where the model predicts the same label as the nearest neighbor in the training data, leading to poor generalization performance. Fixes to Challenge 4. Increase K. Increase the number of neighbors to smooth out the decision boundary and reduce the impact of noisy data. Regularization. Apply regularization techniques like L1 or L2 regularization to penalize complex decision boundaries and prevent overfitting. Challenge 5. Cold start problem. The KNN model performs poorly for new data points that are far from any existing training points. Sample use case that resulted in Challenge 5. A KNN model trained on images of cats and dogs, where it fails to classify a new image of a bird, as there are no similar images in the training dataset. Fixes to Challenge 5. Active learning. Actively select new data points for labeling that are most informative for improving the model's performance on unseen data. Data augmentation. Generate synthetic data points similar to existing training points to expand the coverage of the training dataset. sklearn. Neighbors. Ball tree. Description. The ball tree class in scikit-learn implements a ball tree data structure for efficient nearest neighbor search in multidimensional spaces. It partitions the data points into a hierarchical tree, where each node represents a region ball in the feature space. The tree is constructed recursively by dividing the data points into two subregions based on the distance to the center of the ball. This partitioning continues until the number of points in each region is below a certain threshold. Inputs. X. A 2D array of shape n samples. N features representing the data points for which the ball tree will be built. Each row corresponds to a data point, and each column represents a feature. Metric. A string or callable object specifying the distance metric to use for calculating distances between points. The default is Minkowski, which corresponds to the Euclidean distance. Other options include Manhattan, Chebyshev, cosine, etc. Outputs. Self. The ball tree object itself, which can be used for subsequent nearest neighbor search operations. Steps. Construction. The ball tree is constructed based on the provided data points and distance metric. This involves recursively partitioning the data points into balls until a certain threshold is reached. Search. Once constructed, the ball tree can be used to find the nearest neighbors of a given query point. This is done by traversing the tree, starting from the root node and recursively checking the balls that are closest to the query point. Metrics. Distance metrics. The ball tree supports various distance metrics, allowing users to choose the most appropriate one for their data and application. Common metrics include Euclidean distance, Manhattan distance, Chebyshev distance, and cosine distance. Visualization plots. Ball tree structure. The ball tree can be visualized as a hierarchical tree structure, where each node represents a ball containing data points. This visualization can be helpful in understanding the partitioning of the data space. Fine-tune parameters. Leaf size. The maximum number of points allowed in a leaf node. Smaller leaf sizes can lead to more accurate results but may increase construction time. Metric params. Additional parameters to pass to the distance metric function. Uncertainty methods. Nearest neighbor distance. The distance to the nearest neighbor can provide an indication of uncertainty in the prediction. A larger distance suggests greater uncertainty. Challenges and fixes. Challenge 1. High dimensionality. For very high dimensional data, the performance of the ball tree can degrade due to the curse of dimensionality. This can lead to inefficient search times. Sample use case that resulted in challenge 1. A dataset with hundreds or thousands of features may experience slow nearest neighbor search due to the increased complexity of the ball tree. Fixes to challenge 1. Dimensionality reduction techniques like principal component analysis (PCA) or feature selection can reduce the number of features, making the ball tree more efficient. Approximate nearest neighbor search algorithms like KD-tree or random projection can be used to find approximate nearest neighbors, which can be faster for high-dimensional data. Challenge 2. Memory usage. The ball tree can consume significant memory, especially for large datasets. Sample use case that resulted in challenge 2. A dataset with millions of data points may require a large amount of memory to store the ball tree structure. Fixes to challenge 2. Memory-efficient data structures. Compressed or sparse representations of the ball tree can reduce memory usage. Out-of-core algorithms. Algorithms that operate on data that is stored on disk rather than in memory can be used to handle large datasets. sklearn. Neighbors. KD-tree. Description. A KD-tree is a data structure used for organizing points in a multidimensional space, enabling efficient nearest neighbor search and range queries. It divides the data space into rectangular regions cells recursively, splitting along the dimension with the largest variance at each level. Each node in the KD-tree represents a cell, and the data points within that cell are stored at the leaves. Inputs. X. A NumPy array representing the data points. Each row corresponds to a single data point, and each column corresponds to a dimension. Leaf size. An integer specifying the maximum number of data points to store in a leaf node. The default value is 30. Outputs. KD-tree object. The fitted KD-tree object that can be used for nearest neighbor search and range queries. Steps. Initialization. Create a KD-tree object with the input data points and the optional leaf size. Tree construction. The KD-tree algorithm recursively splits the data space into cells, selecting the dimension with the largest variance at each level and splitting along the median value of that dimension. Metrics. Euclidean distance. The most common distance metric used in KD-tree searches. Calculating the straight line distance between 2 points. Visualization plots. Scatter plot. A scatter plot of the data points can visualize the distribution of points and partitioning of the space by the KD-tree. Fine-tune parameters. Leaf size controls the number of data points in each leaf node, impacting the trade-off between memory usage and search efficiency. Smaller leaf sizes lead to more balanced trees and faster searches, but they also consume more memory. Uncertainty methods. K-nearest neighbors. This method uses the distances to the k-nearest neighbors to estimate k. Uncertainty in the prediction. Challenges and fixes. Curse of dimensionality. As the dimensionality of the data increases, the effectiveness of KD tree searches can decline due to the exponential growth of the search space. Sample use case that resulted in challenge 1: performing nearest neighbor search in a high-dimensional space with a KD tree may result in slow search times and poor accuracy. Fixes to challenge 1. Dimensionality reduction. Employ techniques like principal component analysis (PCA) to reduce the dimensionality of the data before constructing the KD tree. Approximate nearest neighbors. Utilize approximate nearest neighbor search algorithms like ANOV or HNSW, which trade accuracy for speed in high-dimensional spaces. Data skewness. If the data is heavily skewed, the KD tree may not partition the space effectively, leading to unbalanced trees and inefficient searches. Sample use case that resulted in challenge 2: when dealing with data with highly uneven distributions. The KD tree might create very deep branches in some regions while leaving other regions sparsely populated. Fixes to challenge 2. Data preprocessing. Normalize or standardize the data to mitigate the effects of skewness and improve tree balance. Alternative data structures. Consider using other data structures like ball trees or cover trees, which are better suited for handling skewed data. sklearn. Neighbors. Kernel density. Description. A non-parametric method for density estimation. It works by placing a kernel function, e.g. Gaussian, at each data point and summing the kernels to estimate the probability density. Inputs. X. The training data used to fit the model. Shape. N samples. N features. Bandwidth. The width of the kernel function. This is a key parameter that controls the smoothness of the density estimate. Outputs. ScoSamples returns the log density for each sample in X. Sample generates random samples from the estimated density. Steps. Fit the model to the training data X. Determine the probability density at any point based on the kernel function and the distances to the training points. Metrics. Log likelihood score measures the fit of the model to the training data. Cross-validation score evaluates the performance of the model on unseen data. Visualization plots. Density plot visualizes the estimated probability density function. Contour plot plots the contours of the estimated density function. Fine-tune parameters. Bandwidth controls the smoothness of the density estimate. Larger bandwidth leads to smoother estimates. Kernel. The kernel function used to estimate the density. Common options are Gaussian, Epernechnikov, and Top Hat. Uncertainty methods. Bootstrap. Estimate uncertainty by resampling the data and fitting multiple models. Cross-validation. Estimate uncertainty by evaluating the model on different subsets of the data. Challenges and fixes. Challenge 1: choosing the optimal bandwidth. A bandwidth that is too small can lead to overfitting, while a bandwidth that is too large can lead to underfitting. Sample use case that resulted in challenge 1: fitting a kernel density estimator with a bandwidth that is too small to a dataset with many outliers. This results in a highly irregular density estimate that does not accurately reflect the underlying distribution. Fixes to challenge 1: use cross-validation to find the optimal bandwidth. Consider using adaptive bandwidth techniques that vary the bandwidth based on the density of the data. Challenge 2: handling high-dimensional data. As the dimensionality of the data increases, it becomes more difficult to estimate the density accurately. Sample use case that resulted in challenge 2 fitting a kernel density estimator with a large number of features. This can result in a density estimate that is overly smooth and does not capture the true distribution of the data. Fixes to challenge 2: consider using dimension reduction techniques to reduce the dimensionality of the data before fitting the model. Experiment with different kernel functions to find one that is better suited to high-dimensional data. sklearn. Neighbors. K-neighbors classifier. Description. The K-neighbors classifier is a non-parametric, lazy learning algorithm used for classification. It predicts the class of a new data point based on the classes of its k nearest neighbors in the training data. The algorithm stores all training data and classifies new data points by comparing them to the existing data points. It works by finding the k closest training samples to a new data point using a distance metric, e.g., Euclidean distance, and then predicting the class of the new data point based on the majority class among its k neighbors. Inputs: X, a 2D array of shape n samples. N features representing the training data, where each row represents a sample and each column represents a feature. Y, a 1D array of shape n samples, representing the target labels for the training data, where each element corresponds to the class label of the respective sample in X. Outputs: YPRED, a 1D array of shape n samples, representing the predicted class labels for the new data points. Probabilities: a 2D array of shape n samples, n classes representing the probability estimates for each class, where each row corresponds to a new data point and each column corresponds to a class. Steps: training. The algorithm stores all training data points along with their corresponding class labels. Prediction: when a new data point is presented for classification, the algorithm calculates the distance between the new data point and all training data points. Identifies the k nearest neighbors to the new data point based on the calculated distances. Determines the majority class among the k nearest neighbors. Assigns the majority class as the predicted class for the new data point. Metrics: accuracy, the proportion of correctly classified instances. Precision, the proportion of correctly predicted positive instances out of all instances predicted as positive. Recall, the proportion of correctly predicted positive instances out of all actual positive instances. F1 score, the harmonic mean of precision and recall. Visualization plots. Decision boundary plot visualizes the decision boundary separating different classes in the feature space. Scatter plot shows the distribution of data points in the feature space, color-coded by their classes. Fine-tune parameters. N neighbors, the number of neighbors to consider for classification. Weights, the weighing scheme used to weigh the contributions of neighbors. Options include uniform, all neighbors contribute equally. Distance, neighbors closer to the new data point have more weight. Algorithm, the algorithm used to compute the nearest neighbors. Options include auto attempts to decide the most appropriate algorithm based on the values passed to fit method. Ball tree uses ball tree algorithm for nearest neighbor search. KD tree uses KD tree algorithm for nearest neighbor search. Brute uses brute force search for nearest neighbor search. Metric, the distance metric used to calculate the distance between data points. Options include Euclidean distance, Manhattan distance, Minkowski distance. Uncertainty methods. Confidence score, the probability of the predicted class, providing a measure of uncertainty. Challenges and fixes. Challenge 1: Curse of dimensionality, performance degradation in high-dimensional spaces due to sparse data distribution. Sample use case that resulted in Challenge 1: classifying images using pixel values as features. Fixes to Challenge 1. Feature selection: reduce the number of features by selecting the most relevant ones. Dimensionality reduction: apply techniques like principal component analysis (PCA) to reduce dimensionality while preserving important information. Challenge 2: sensitivity to outliers. Outliers can significantly impact the prediction, especially when using a small value of k. Sample use case that resulted in Challenge 2: a data point with an unusual feature value can influence the classification of its neighbors. Fixes to Challenge 2. Robust distance metrics: use distance metrics less sensitive to outliers, like Manhattan distance. Outlier detection: identify and remove outliers from the training data. Challenge 3: computational cost for large datasets. The algorithm can be computationally expensive for large datasets, especially for brute force search. Sample use case that resulted in Challenge 3: classifying millions of data points with high dimensionality. Fixes to Challenge 3. Approximate nearest neighbor search: use approximate nearest neighbor search algorithms to reduce computational time. Tree-based methods utilize efficient tree-based data structures like ball tree or KD tree for faster neighbor search. sklearn. Neighbors. K-neighbors regressor. Description. K-neighbors regressor is a non-parametric, lazy learning algorithm used for regression tasks in machine learning. It operates based on the principle of k-nearest neighbors, where it predicts the output value for a new data point based on the values of its k-nearest neighbors in the training dataset. Inputs. X. This is the input feature matrix containing the training data. Each row represents a data point, and each column represents a feature. Y. This is the target variable array containing the corresponding output values for each data point in the training set. Outputs. YPRED. This is the array of predicted output values for the given input data. Model. This is the trained k-neighbors regressor object. It can be used to make predictions on new data points. Steps. Training. The algorithm first learns from the training data by storing all the data points and their corresponding target values in memory. Prediction. When a new data point is given, the algorithm identifies the k-nearest neighbors to the new data point based on a chosen distance metric. It then calculates the predicted output value by averaging the target values of the k-nearest neighbors, weighted by their distance from the new data point. Metrics. Mean squared error MSE measures the average squared difference between the predicted and actual target values. Root mean squared error RMSE, the square root of MSE, providing a more interpretable measure of prediction error. R squared R indicates the proportion of variance in the target variable that is explained by K. Model. Visualization plots. Scatter plot plots the actual target values versus the predicted values to visualize the models. Performance. Residual plot plots the difference between the actual and predicted values residuals against K. Predicted values to check for patterns or trends. Fine-tune parameters. N neighbors, the number of neighbors to consider during prediction. Higher values can smooth out predictions but may lead to overfitting. Weights specifies how to weigh the contribution of each neighbor. Uniform gives equal weight to all neighbors, while distance weights neighbors by their inverse distance. Metric. The distance metric used to calculate the distance between data points. Common options include Euclidean, Manhattan, and Minkowski. P. The power parameter for the Minkowski metric. P1 corresponds to Manhattan distance, while P2 corresponds to Euclidean distance. Uncertainty methods. Confidence intervals can be calculated for the predictions by considering the spread of P. Target values among the K nearest neighbors. Challenges and fixes. Challenge 1. Overfitting the model can overfit to the training data, leading to poor performance on unseen data. Sample use case. Using a small value for n neighbors or a complex distance metric may cause overfitting. Fixes. Increase n neighbors to smooth out predictions. Use a simpler distance metric, such as Euclidean distance. Employ techniques like cross-validation to assess model performance on unseen data and avoid overfitting. Challenge 2. Sensitivity to outliers. The model can be sensitive to outlier data points, which can disproportionately influence the predictions. Sample use case. An outlier data point can be assigned a large weight if distance weighing is used. Fixes. Pre-process the data to remove or handle outliers. Use robust distance metrics that are less sensitive to outliers. Consider alternative algorithms like random forest regressor, which are less susceptible to outliers. Challenge 3. Curse of dimensionality. The model's performance can degrade as the number of features increases, making it difficult to find truly close neighbors in high-dimensional spaces. Sample use case. With many features, the distance between data points becomes less meaningful. Fixes. Perform feature selection or dimensionality reduction to reduce the number of features. Use different distance metrics that are more suitable for high-dimensional data. Consider alternative algorithms that are better suited for high-dimensional data, such as support vector machines. sklearn. Neighbors. K-neighbors transformer. Description. The K-neighbors transformer class in scikit-learn. sklearn is a transformer that uses K-nearest neighbors KNN to transform data. It leverages the idea that similar data points tend to be close to each other in a multi-dimensional space. The transformer can be used for dimensionality reduction, feature extraction, and imputation of missing values. Inputs. X. The input data, typically a NumPy array or pandas data frame containing numerical features. N neighbors. The number of nearest neighbors to consider for each data point. This parameter controls the locality of the transformation. Outputs. Transformed X. The transformed data, which has the same number of rows as the input data but a potentially different number of columns. The transformed features are based on the distances to the K nearest neighbors. Steps. For each data point in the input data, identify its K nearest neighbors based on a distance metric, e.g. Euclidean distance. Calculate a new set of features for each data point based on the distances to its K nearest neighbors. The specific transformation depends on the chosen method. Distance. The distances to the K nearest neighbors are used directly as features. Mean. The average of the features of the K nearest neighbors is used as the transformed feature. Median. The median of the features of the K nearest neighbors is used as the transformed feature. Max. The maximum of the features of the K nearest neighbors is used as the transformed feature. Min. The minimum of the features of the K nearest neighbors is used as the transformed feature. Metrics. No specific metrics are inherent to the K neighbors transformer itself. However, you can evaluate the effectiveness of the transformation based on the performance of subsequent machine learning models, e.g. classifiers. Regresses that use the transformed data. Visualization plots. Scatter plots visualize the transformed data points in a reduced dimensionality space if the number of features is small enough. You can use different colors to represent different classes or labels in a supervised setting. Heat maps. If the transformed features are distances, you can create heat maps to visualize the distance relationships between data points. Fine-tune parameters. N neighbors. The number of neighbors to consider. Increasing this parameter can make the transformation more robust but can also introduce bias if the data is not uniformly distributed. Weights. The weighing scheme for the neighbors. By default, all neighbors have equal weight uniform. You can use distance to give more weight to closer neighbors, which can be useful for non-uniform data. Metric. The distance metric to use for finding nearest neighbors. Options include Euclidean default, Manhattan, cosine, Minkowski algorithm. The algorithm used to find the nearest neighbors. Options include brute default, ball tree, KD tree, auto, leaf size. The size of the leaves in the ball tree or KD tree. Smaller values can lead to faster queries but can also increase memory usage. Uncertainty methods. No inherent uncertainty methods are provided by K-neighbors transformer. You can use external methods like confidence intervals or Bayesian inference to estimate the uncertainty in the transformed features. Challenges and fixes. Challenge 1. Curse of dimensionality in high-dimensional spaces. The distances between data points become less meaningful and the effectiveness of KNN can decrease. This can result in inaccurate transformations. Sample use case. Transforming data with hundreds or thousands of features using a standard KNN method might lead to poor results. Fixes. Dimensionality reduction techniques. Use techniques like PCA or TSNE to reduce the number of features before applying K-neighbors transformer. Feature selection. Select the most relevant features for the task at hand before transformation. Challenge 2. Data imbalance. If the data is imbalanced, the nearest neighbors of data points in the minority class may be dominated by points from the majority class, leading to biased transformations. Sample use case. Using K-neighbors transformer on data with a large class imbalance might lead to overfitting to the majority class and poor performance on the minority class. Fixes. Oversampling. Increase the number of data points in the minority class using techniques like SMORT. Undersampling. Reduce the number of data points in the majority class using techniques like random undersampling or Tomek links. Weighted KNN. Use weighted KNN methods that give more weight to neighbors from the minority class. sklearn. Neighbors. Local outlier factor. Description. The local outlier factor (LOF) algorithm is an unsupervised anomaly detection technique that identifies outliers in a dataset based on their local density deviation. It measures the local density deviation of a data point with respect to its neighbors. If a data point has a significantly lower density compared to its neighbors, it is considered an outlier. Inputs. X a 2D array of shape n samples. N features. Representing the input dataset where each row is a data point and each column is a feature. N neighbors. An integer representing the number of nearest neighbors to consider for each data point. It influences the size of the local neighborhood used for density estimation. Outputs. Negative outlier factor a 1D array of shape n samples, representing the LOF scores for each data point. Higher scores indicate a higher degree of outlierness. Labels a 1D array of shape n samples, containing labels for each data point. 1 represents outliers, -1 represents inliers, and 0 represents borderline points. Steps 1. Nearest neighbor calculation. The algorithm calculates the k nearest neighbors for each data point in the dataset, where k is specified by the n neighbors parameter. 2. Local reachability density for each data point. The algorithm computes the local reachability density LRD, which measures the density of the neighborhood surrounding the data point. 3. Local outlier factor calculation. The LOF score for each data point is calculated by comparing its LRD to the LRD of its neighbors. If a data point has a significantly lower LRD than its neighbors, it is considered an outlier, resulting in a higher LOF score. Metrics. Precision. The proportion of correctly identified outliers among all identified outliers. Recall the proportion of correctly identified outliers among all actual outliers. F1 score. The harmonic mean of precision and recall. Visualization plots. Scatter plots visualizing the data points with different colors or sizes representing their LOF scores can reveal outliers as data points with distinct visual patterns. Density plots. Plotting the distribution of LOF scores helps identify the threshold for separating outliers from inliers. Fine-tune parameters. N neighbors. The number of neighbors to consider for each data point. A larger value means considering a broader neighborhood, potentially capturing subtle outliers. Leaf size. The size of the leaf nodes in the KD tree used for nearest neighbor search. A smaller value leads to more precise neighbor searches but can increase computation time. Algorithm. The algorithm used for nearest neighbor search, which can be auto, ball tree, KD tree, or brute. Uncertainty methods. Confidence interval computing. A confidence interval for the LOF scores can provide insights into the uncertainty in the outlier identification. Sensitivity analysis. Varying the n neighbors parameter and observing the changes in the LOF scores can reveal the sensitivity of the results to neighborhood size. Challenges and fixes. Challenge 1. Sensitivity to neighborhood size. The choice of n neighbors can significantly impact the LOF scores, potentially leading to misclassification of outliers. Sample use case. In a dataset with a highly clustered structure, a small n neighbors value might fail to identify outliers that are in low-density regions outside the clusters. Fixes to challenge 1. Try different values of n neighbors to find the optimal setting for the specific dataset. Use cross-validation or grid search to find the best n neighbors value for a given dataset. Challenge 2. Handling high-dimensional data in high-dimensional spaces. Distance calculations become less meaningful, and the LOF algorithm might struggle to identify outliers effectively. Sample use case. In a dataset with hundreds of features, LOF might fail to capture the local density variations due to the curse of dimensionality. Fixes to challenge 2. Apply dimensionality reduction techniques like PCA or TSNE before applying LOF to reduce the dimensionality of the data. Use alternative outlier detection techniques designed for high-dimensional data, such as isolation forest or one-class SVM. sklearn, neighbors, radius neighbors classifier. Description. A classifier that implements radius-based nearest neighbors search. It predicts the class of a data point based on the majority class among its neighbors within a specified radius. Inputs. X training data, where each row represents a data point and each column represents a feature. Y target labels for the training data. Outputs. Predicted class labels. The predicted class labels for new data points based on the learned Neighborhood structure. Probability is optional. The probability of each class for new data points. Steps. Training. The model learns the neighborhood structure of the training data by storing all data points and their corresponding labels. Prediction for a new data point. The model finds all training data points within a specified radius. It then predicts the class of the new data point based on the majority class among its neighbors. Metrics. Accuracy. The percentage of correctly classified data points. Precision. The ratio of true positive predictions to the total number of positive predictions. Recall. The ratio of true positive predictions to the total number of actual positive instances. F1 score. A harmonic mean of precision and recall. Visualization plots. Decision boundary plot visualizes the decision boundary learned by the model. Neighborhood visualization visualizes the neighbors of a specific data point. Fine-tune parameters. Radius. The radius of the neighborhood to consider for predictions. Weights. The weight function to use for neighbors, e.g. uniform. Distance. Algorithm. The algorithm to use for neighbor search, e.g. brute, KD tree, ball tree. Uncertainty methods. Confidence score. The probability of the predicted class. Number of neighbors. The number of neighbors within the specified radius. Challenges and fixes. Challenge 1. Choosing the optimal radius. A radius that is too small may result in few neighbors, leading to inaccurate predictions. A radius that is too large may include irrelevant neighbors, also leading to inaccurate predictions. Sample use case that resulted in challenge 1. A model with a small radius failed to predict the class correctly for a new data point that was located close to the decision boundary. Fixes to challenge 1. Experiment with different radius values to find the optimal balance between including enough neighbors and avoiding irrelevant neighbors. Challenge 2. Handling imbalanced datasets. If the data is imbalanced, the model may favor the majority class. Sample use case that resulted in challenge 2. A model trained on an imbalanced dataset consistently predicted the majority class for new data points. Fixes to challenge 2. Oversample the minority class or undersample the majority class to balance the dataset. Use a weighted loss function to penalize misclassifications of the minority class more heavily. sklearn. Neighbors. Radius neighbors regressor. Description. Radius neighbors regressor implements a regression model based on k nearest neighbors. Instead of using a fixed number of neighbors, it considers all neighbors within a specified radius from the query point. This approach allows for more flexibility and adaptability to the density of the data. Inputs. X. This is the training input samples. It can be a 2D array-like structure containing the features for each data point. Y. This is the target values for the training data corresponding to the input samples in X. It should be a 1D array-like structure. Outputs. YPRED. This is the predicted target values for the new input samples. It is a 1D array-like structure with the same length as the number of input samples. Weights. This is an array of weights associated with each sample in the neighborhood. These weights are used to compute the weighted average prediction. Steps. 1. For each query point, it identifies all the neighbors within the specified radius. 2. It then computes the weighted average of the target values of these neighbors. The weights are determined based on the distance from the query point. Metrics. Mean squared error MSE. This measures the average squared difference between the predicted and actual target values. R squared R2. This indicates the proportion of variance in the target variable that is explained by the model. Visualization plots. Scatter plot with regression line. This visualizes the relationship between the input features and the target variable, highlighting the fitted regression line. Residual plot. This plot displays the difference between the predicted and actual target values, helping to assess the model's accuracy. Fine-tune parameters. Radius. This parameter defines the radius within which neighbors are considered for prediction. A larger radius includes more neighbors but may introduce noise. A smaller radius might miss relevant neighbors but reduces noise. Weights. This parameter controls the weighing scheme used to compute the weighted average. Prediction. Common options are uniform. All neighbors have equal weight and distance weights are inversely proportional to the distance. Outlier label. This parameter specifies the value to assign to data points that have no neighbors within the specified radius. Uncertainty methods. Confidence intervals. These can be estimated based on the distribution of the target values in a neighborhood. Bootstrap resampling. This involves repeatedly sampling with replacement from the training data to estimate the prediction variance and provide uncertainty bounds. Challenges and fixes. Challenge 1. Choosing the optimal radius. Sample use case that resulted in challenge 1. If the radius is too small, the model might miss relevant neighbors, leading to underfitting. If the radius is too large, it might include irrelevant neighbors, introducing noise and overfitting. Fixes to challenge 1. You can experiment with different radii using cross-validation and choose a radius that results in the best performance on the validation set. Challenge 2. Handling data with varying density. Sample use case that resulted in challenge 2. If the data density is highly uneven, the model's performance might be inconsistent across different regions. Fixes to challenge 2. You can consider using adaptive radii or employing techniques like density-based clustering to adjust the neighborhood size based on the local data density. sklearn. Neighbors. Radius neighbors transformer. Description. The radius neighbors transformer is a class in scikit-learn that transforms data by replacing each sample with its k nearest neighbors within a specified radius. It's useful for imputing missing values, denoising, and creating a smoother representation of the data. Inputs. X. This is the input data. Typically a 2D array where each row represents a sample and each column represents a feature. Radius. This parameter defines the radius around each sample within which to consider neighbors. It controls the locality of the transformation. Outputs. Transformed X. This is the output data. A 2D array with the same dimensions as X, where each sample has been replaced by the average of its neighbors within the specified radius. Neighbors indices. This is a 2D array where each element contains the indices of the neighbors for the corresponding sample in X. Steps. 1. Find neighbors for each sample in X. The algorithm searches for all other samples within a specified radius. 2. Calculate weighted average. The transformed value for each sample is computed as a weighted average of its neighbors within the radius. The weights can be uniform equal weight for all neighbors or based on distance closer neighbors have higher weights. Metrics. Mean squared error MSE. This metric measures the average squared difference between the original and transformed data points. It can be used to evaluate the performance of the radius neighbors transformer in terms of data reconstruction. Root mean squared error RMSE. This is the square root of the MSE and provides a more interpretable measure of the average difference between the original and transformed data. Visualization plots. Scatter plot. A scatter plot can visualize the original data and the transformed data, showing how the radius neighbors transformer modifies the data points. Fine-tune parameters. Radius. This is the most important parameter to tune. A larger radius will include more neighbors and result in a smoother transformation. A smaller radius will focus on local neighborhoods and potentially preserve more detail in the data. Metric. This parameter controls the distance metric used to find neighbors. Different metrics can be suitable for different data types and applications. Common options include Euclidean, Manhattan, and cosine. Weights. This parameter specifies the weighing scheme used for calculating the weighted average of neighbors. Uniform assigns equal weights to all neighbors. Distance assigns weights inversely proportional to the distance from the target sample. Uncertainty methods. Confidence intervals. Confidence intervals can be estimated for the transformed data based on uncertainty in the neighbor selection process. Challenges and fixes. Challenge 1. Sparse data. When data is sparse, finding neighbors within a fixed radius can be challenging. This can lead to inaccurate transformation results. Sample use case that resulted in challenge 1. A dataset with many missing values or a dataset with high dimensionality can be considered sparse. Fixes to challenge 1. Consider using a different distance metric that is more appropriate for sparse data, such as the Jacquard distance. Experiment with different radius values to find an appropriate balance between finding enough neighbors and avoiding overfitting. Challenge 2. High-dimensional data. Finding neighbors in high-dimensional space can be computationally expensive and might result in poor performance. Sample use case that resulted in challenge 2. A dataset with hundreds or thousands of features could lead to this challenge. Fixes to challenge 2. Consider using dimensionality reduction techniques, such as PCA, before applying the radius neighbors transformer. Choose a distance metric that is robust to high dimensionality, such as the cosine distance. Challenge 3. Outlier detection. Outliers can significantly affect the transformation process. If a single outlier is within the radius of a sample, it can heavily influence the transformed value. Sample use case that resulted in challenge 3. A dataset with a few extremely unusual samples could lead to this problem. Fixes to challenge 3. Pre-process the data to remove or handle outliers before using the radius neighbors transformer. Use outlier robust distance metrics or weighing schemes to mitigate the influence of outliers. sklearn. Neighbors. Nearest centroid. Description. Nearest centroid is a classifier that uses the mean of the samples in each class as the centroid for that class. When predicting the class of a new sample, it finds the centroid closest to that sample and assigns the class of that centroid. This method is simple and efficient, particularly for high-dimensional data. Inputs. X. The training input samples. As a 2D array of shape n samples. N features. Y. The target values. As a 1D array of shape n samples. Outputs. Self. The fitted nearest centroid object. PredictX. The predicted class labels for the input samples X. Steps. Training. The algorithm computes the mean of the features for each class in the training data. This mean becomes the centroid for that class. Prediction. Given a new sample, the algorithm calculates the Euclidean distance between the sample and each centroid. The class of the closest centroid is assigned as the prediction for the new sample. Metrics. Accuracy. The percentage of correctly classified samples. Precision. The ratio of true positives to the sum of true positives and false positives. Recall. The ratio of true positives to the sum of true positives and false negatives. F1 score. The harmonic mean of precision and recall. Visualization plots. Scatter plot. This plot shows the distribution of data points and the centroids for each class. Decision boundary. This plot shows the boundaries that separate different classes based on pay. Nearest centroid rule. Fine-tune parameters. Metric. The distance metric to use for finding the nearest centroid. Common options include Euclidean, Manhattan, and cosine. Shrink threshold controls the shrinkage of the centroids towards the grand mean. A higher value shrinks the centroids more. Uncertainty methods. Distance to centroid. The distance of a sample from its nearest centroid can be used as a measure of uncertainty. Higher distances indicate greater uncertainty in the prediction. Challenges and fixes. Challenge 1. Outlier samples. Outliers in the training data can significantly shift the centroids, leading to inaccurate predictions. Sample use case that resulted in challenge 1. A training dataset containing a few very large values in a specific feature. These outliers might pull the centroid for that class towards them, even if they represent a small portion of the data. Fixes to challenge 1. Data preprocessing. Consider outlier detection techniques, e.g., Z-score, IQR, and remove or cap outliers before training. Robust estimators. Use robust estimators for computing the centroids, e.g., trimmed mean, that are less sensitive to outliers. Challenge 2. Nonlinear data. Nearest centroid assumes linear separability between classes. It may not perform well when classes are highly nonlinear or overlapping. Sample use case that resulted in challenge 2. A dataset where two classes form concentric circles, making it difficult to separate them linearly. Fixes to challenge 2. Feature engineering. Create new features that capture nonlinear relationships. Nonlinear models. Consider using more sophisticated nonlinear models, e.g., support vector machines. Decision trees for these cases. sklearn. Neighbors, nearest neighbors. Description. The nearest neighbors class in scikit-learn is a powerful tool for finding the closest neighbors to a given point in a dataset. It uses various distance metrics to determine the similarity between points and offers several methods for finding neighbors based on specified parameters. Inputs. X. This is a 2D array containing the data points. Each row represents a data point, and each column represents a feature. N neighbors. This integer parameter specifies the number of nearest neighbors to retrieve. Outputs. The neighbors. This method returns the indices of the k nearest neighbors for each point in the input. Data. The neighbors graph. This method returns a sparse graph representing the k nearest neighbors for each point. Radius. Neighbors. This method returns the indices of neighbors within a given radius from each point in the input data. Radius. Neighbors graph. This method returns a sparse graph representing the neighbors within a given radius from each point. Steps. Initialization. The nearest neighbors object is initialized with parameters like the number of neighbors, n neighbors, and the distance metric to be used. Fitting the model. The fit method is called with the input data x to train the model. This step involves storing the data points and computing any necessary pre-processing steps based on the distance metric. Finding nearest neighbors. The k-neighbors, the neighbors graph, radius neighbors, and radius neighbors graph methods are used to retrieve the neighbors based on the specified parameters. Metrics. Euclidean distance. This is the most common distance metric and calculates the straight line distance between 2 points. Manhattan distance. This metric calculates the sum of absolute differences between the corresponding coordinates of 2 points. Minkowski distance. This is a generalization of Euclidean and Manhattan distances that uses a parameter p to control the degree of influence of each dimension. Cosine distance. This metric measures the angle between two vectors, where a smaller angle indicates higher similarity. Visualization plots. Scatter plots. These plots can be used to visualize the data points and highlight the nearest neighbors. K-nearest neighbor graphs. These graphs connect each data point to its k-nearest neighbors, providing a visual representation of the neighborhood structure. Fine-tune parameters. N neighbors. This parameter controls the number of nearest neighbors to find. Algorithm. This parameter specifies the algorithm used to find neighbors, e.g. ball tree, KD tree, brute, leaf size. This parameter influences the efficiency of tree-based algorithms, e.g. ball tree, KD tree. Metric. This parameter allows the user to choose the distance metric to be used. P. This parameter is used for the Minkowski distance metric and controls the degree of influence of each dimension. Uncertainty methods. Confidence scores. These scores can be used to assess the reliability of neighbor predictions. Distance-based uncertainty. This method considers the distance between a point and its nearest neighbors to quantify uncertainty. Ensemble methods. Using multiple nearest neighbors models with different parameters can provide an ensemble prediction and associated uncertainty measures. Challenges and fixes. Challenge 1. Curse of dimensionality in high-dimensional spaces. The distance between points becomes less meaningful, making it difficult to find accurate neighbors. Sample use case that resulted in challenge 1. Using nearest neighbors to classify images with a large number of pixels. Features can be problematic due to the curse of dimensionality. Fixes to challenge 1. Dimensionality reduction techniques. Apply methods like principal component analysis (PCA) or TSNE to reduce the number of dimensions while preserving important information. Feature selection. Select the most relevant features for the task, reducing the number of dimensions and improving the accuracy of nearest neighbor search. Challenge 2. Computational complexity. Finding nearest neighbors in large datasets can be computationally expensive, especially for algorithms like brute force search. Sample use case that resulted in challenge 2. Searching for nearest neighbors in a dataset with millions of data points using brute force search can be time-consuming. Fixes to challenge 2. Tree-based algorithms. Employ ball tree or KD tree algorithms for faster neighbor search, especially for large datasets. Approximate nearest neighbors. Utilize algorithms like locality-sensitive hashing (LSH) to efficiently find approximate nearest neighbors, trading off accuracy for speed. Challenge 3. Handling outliers. Outliers can significantly affect the performance of nearest neighbor algorithms, leading to inaccurate predictions. Sample use case that resulted in challenge 3. In a dataset containing a few outlier points, nearest neighbor algorithms might incorrectly assign neighbors to these outliers, leading to incorrect predictions. Fixes to challenge 3. Outlier detection and removal. Apply outlier detection techniques to identify and remove outliers before training the nearest neighbors model. Robust distance metrics. Use distance metrics that are less sensitive to outliers, like the Manhattan distance. Challenge 4. Handling imbalanced datasets. In imbalanced datasets where one class has significantly more data points than others, nearest neighbor algorithms can be biased towards the majority class. Sample use case that resulted in challenge 4. In a dataset where 90 of the data belongs to one class and 10 to another, the nearest neighbors model might predict all points as belonging to the majority class, ignoring the minority class. Fixes to challenge 4. Oversampling or undersampling. Apply techniques like oversampling the minority class or undersampling the majority class to balance the dataset and improve the performance of nearest neighbor algorithms. Cost-sensitive learning. Assign different costs to misclassification errors based on the class imbalance. sklearn, neighbors, neighborhood components analysis. Description: a dimensionality reduction method that learns a projection to a lower dimensional space that preserves the neighborhood structure of the data. It uses a nearest neighbors search to find the neighborhood of each data point and projects the data to a lower dimensional space that minimizes the distortion of these neighborhoods. Inputs: X the training input samples, where n samples is the number of samples and n features is the number of features. N components the number of components or dimensions to project onto. This parameter controls the dimensionality of the output space. Outputs: components the projection matrix learned by the algorithm. It has shape n features. N components and represents the transformation that maps the original data to the lower dimensional space. N features in number of features seen during fit. Feature names and names of features seen during fit. Defined only when X has feature names that are all strings. Steps: the algorithm first constructs a neighborhood graph where each data point is connected to its k nearest neighbors. It then learns a projection matrix that minimizes the distortion of this neighborhood structure. This is achieved by finding a projection that minimizes the difference between the distances in the original high dimensional space and the distances in the projected lower dimensional space. Metrics: reconstruction error. This metric measures the difference between the original data and the reconstructed data after projection and back projection. It can be used to assess the quality of the dimensionality reduction. Visualization plots: scatter plot. This can be used to visualize the data in the original and projected spaces. This helps to understand how the neighborhood structure is preserved in the lower dimensional space. Fine-tune parameters: n components. This parameter controls the dimensionality of the output space and needs to be carefully chosen based on the desired level of dimensionality reduction and the trade-off between accuracy and complexity. N neighbors. This parameter determines the size of the neighborhood used for constructing the neighborhood graph. A higher value for n neighbors leads to larger neighborhoods and potentially smoother projections. Uncertainty methods: confidence intervals. Confidence intervals can be estimated for the projected data points to quantify the uncertainty in the projection. Challenges and fixes: Challenge 1: high dimensionality of the input data can lead to computational challenges in constructing the neighborhood graph. Sample use case that resulted in challenge 1 when dealing with very high dimensional datasets, such as image data. Calculating the distances between all data points to find the nearest neighbors can be computationally expensive and time-consuming. Fixes to challenge 1: approximate nearest neighbor search. Algorithms use techniques like KD trees, ball trees, or locality-sensitive hashing to approximate the nearest neighbors and reduce the computational burden. Random projection: apply random projection methods to reduce the dimensionality of the input data before constructing the neighborhood graph, making the nearest neighbor search faster. Challenge 2: choosing the optimal number of components. N components is crucial for balancing dimensionality reduction and accuracy. Sample use case that resulted in challenge 2: a very low value of n components might lead to excessive data loss, while a very high value might not achieve significant dimensionality reduction. Fixes to challenge 2: reconstruction error. Monitor the reconstruction error as a function of n components and choose the value that gives a good trade-off between dimensionality reduction and error. Visualization: use scatter plots or other visualizations to inspect the data in the projected space and identify an appropriate value for n components that preserves the essential structure of the data. Challenge 3. The choice of the metric used to measure distances between data points can significantly impact the results. Sample use case that resulted in challenge 3. Choosing an inappropriate metric might lead to poor neighborhood preservation in the projected space. Fixes to challenge 3. Domain knowledge. Leverage domain knowledge to choose an appropriate distance metric that reflects the underlying relationships in the data. Experimentation. Experiment with different metrics and evaluate their performance based on pay, reconstruction error, or other relevant metrics. Visualization. Visualize the data in the projected space for different metrics to assess pay, quality of neighborhood preservation, and choose the metric that leads to the most desirable results. Challenge 4. The algorithm might be sensitive to the presence of outliers in the data. Sample use case that resulted in challenge 2. Outliers might distort the neighborhood structure and lead to poor projections. Fixes to challenge 2. Outlier detection. Use outlier detection techniques to identify and remove or adjust outliers before applying the algorithm. Robustness. Explore robust versions of the algorithm that are less susceptible to the influence of outliers. sklearn, neighbors, K-neighbors graph. Description. This function constructs the K-neighbors graph for a given dataset. The graph is represented as a sparse adjacency matrix, where non-zero entries indicate the presence of an edge between two data points. An edge exists between two data points if they are among each other's K nearest neighbors. This function utilizes various distance metrics to determine the nearest neighbors, allowing for flexible graph construction based on the dataset's characteristics. Inputs. X. This input represents the dataset for which the K-neighbors graph is to be constructed. It is a 2D array of shape n samples. N features, where each row represents a data point and each column represents a feature. N neighbors. This parameter determines the number of nearest neighbors to consider for each data point. It directly influences the sparsity of the resulting graph. A higher value of n neighbors leads to a denser graph with more connections between data points. Mode. This parameter specifies the type of graph representation. It can take the values connectivity or distance. If set to connectivity, the adjacency matrix will contain only ones and zeros, indicating the presence or absence of an edge. If set to distance, the adjacency matrix will contain the actual distances between neighbors. Metric. This parameter defines the distance metric used to calculate the distances between data points. It can be a string specifying a supported metric, e.g., Euclidean, Manhattan, cosine, or a user-defined callable function. Includes ELF. This Boolean parameter determines whether to include self-connections in the graph. If set to true, each data point will be considered its own nearest neighbor. Njobs. This parameter controls the number of parallel jobs to run for computations. It allows for parallelization to speed up the process, especially for large datasets. Outputs. This output is a sparse adjacency matrix representing the constructed K-neighbors graph. Its shape is n samples. N samples, where each row and column corresponds to a data point. Non-zero entries in the matrix indicate the presence of an edge between two data points. Steps. For each data point in the input dataset X, the algorithm finds its K nearest neighbors based on the specified distance metric. The algorithm constructs a sparse adjacency matrix A, where each entry AI, J represents the connection between data points I and J. If mode is set to connectivity, the entry AI, J is set to 1 if data point J is among the K nearest neighbors of data point I. and 0 otherwise. If mode is set to distance, the entry ai, j is set to the distance between data points I and j if j is among the k nearest neighbors of I, and 0 otherwise. Metrics. Distance metric. The choice of distance metric significantly influences the resulting graph structure. Different metrics emphasize different aspects of the data, leading to varying graph connectivity and neighborhood relationships. Visualization plots. Graph visualization. The constructed k-neighbors graph can be visualized using graph plotting libraries to understand the relationships and connectivity patterns within the dataset. This visualization can help identify clusters, outliers, and other structural characteristics. Fine-tune parameters. N neighbors. Adjusting the value of n neighbors directly controls the sparsity of the graph. A higher value leads to a denser graph with more connections, potentially capturing more global relationships. A lower value results in a sparser graph, highlighting more localized relationships. Metric. The choice of distance metric can significantly impact the graph structure. Experimenting with different metrics can reveal hidden relationships within the data and improve the accuracy of downstream tasks. Uncertainty methods. None. This function does not directly handle uncertainty estimation. However, by leveraging different distance metrics and analyzing the resulting graph structure, insights into the uncertainty of neighbor relationships can be obtained. For example, a higher number of neighbors or a wider range of distances between neighbors could indicate higher uncertainty in the neighborhood assignment. Challenges and fixes. Challenge 1. Choosing the appropriate distance metric can be challenging, as it directly impacts the neighborhood relationships and the resulting graph structure. Sample use case that resulted in challenge 1 when dealing with data containing both continuous and categorical features. Using a single distance metric might not be optimal, leading to inaccurate neighbor assignments. Fixes to challenge 1. Consider using composite distance metrics that combine different metrics for different feature types. For example, using a weighted combination of Euclidean distance for continuous features and Hamming distance for categorical features. Challenge 2. The computational cost of finding nearest neighbors can be high, especially for large datasets or when using complex distance metrics. Sample use case that resulted in challenge 2 when working with a massive dataset containing millions of data points. Calculating the distances between all pairs can become computationally expensive. Fixes to challenge 2. Explore approximate nearest neighbor search algorithms, such as KD tree or ball tree search, which can efficiently find approximate nearest neighbors without computing all pairwise distances. Utilize efficient data structures and algorithms for distance calculations, such as specialized libraries optimized for specific distance metrics. Consider parallelizing the computations to distribute the workload across multiple cores or processors. sklearn. Neighbors. Radius neighbors graph. Description. This function constructs the k-nearest neighbors graph for a given set of samples. It connects nodes that are within a specified radius of each other in the feature space. Inputs. X. The input data, typically a 2D array of shape n samples. N features, where each row represents a data point. Radius. The radius within which neighbors are considered. Outputs. A sparse graph representing the neighborhood structure. The graph is represented as a sparse adjacency matrix, where each non-zero element indicates a connection between two nodes. The value of each non-zero element is 1, representing an undirected connection. The graph can be visualized using various plotting libraries like Matplotlib. Steps. For each data point in X, it calculates the distances to all other points using a specified distance metric. It then identifies the neighbors within the specified radius. The neighbors are then connected in the graph with an edge weight of 1. Metrics. Distance metric. The choice of distance metric, e.g., Euclidean, Manhattan, Chebyshev, can significantly influence the resulting graph structure. Radius. The choice of radius determines the density of the graph and the number of neighbors for each node. Visualization plots. Graph visualization. The resulting graph can be visualized using plotting libraries like Matplotlib or NetworkX. This visualization allows you to analyze the connectivity patterns and identify clusters or dense regions in the data. Scatter plot. A scatter plot of the data points with the graph edges overlaid can provide a visual understanding of the neighborhood relationships. Fine-tune parameters. Radius. The radius parameter controls the density of the graph. Increasing the radius will lead to more connections and a denser graph, while decreasing it will result in fewer connections and a sparser graph. Metric. The choice of distance metric can significantly impact the graph structure. For example, using a different metric like Manhattan or Chebyshev distances can lead to different neighbor relationships. Uncertainty methods. No explicit uncertainty methods are provided by the function itself. However, you can explore uncertainty in the graph structure by using different values of the radius parameter and observing the changes in the graph. Analyzing the distribution of neighbor counts across nodes and identifying potential outliers or areas with high or low connectivity. Challenges and fixes. Challenge 1. Choosing the appropriate radius parameter can be challenging. Sample use case. If the radius is too small, the graph may be disconnected, with many nodes isolated. If the radius is too large, the graph may become dense, with many connections, making it difficult to identify meaningful relationships. Fixes. Experiment with different values of the radius and visualize the resulting graphs to determine the optimal value. Use techniques like elbow analysis to identify a suitable radius value based on the number of neighbors or the density of the graph. Challenge 2. High-dimensional data can make it difficult to visualize and interpret the resulting graph. Sample use case. In high-dimensional spaces, the notion of distance becomes more complex, and visualizing the graph can be challenging due to the increased complexity. Fixes. Use dimensionality reduction techniques like PCA or TSNE to reduce the dimensionality of data before constructing the graph. Explore alternative visualization methods like force-directed layout algorithms that can help to represent the graph in a more informative way. sklearn. Neighbors. Sort graph by row values. Description. The sort graph by row values function is used to sort a connectivity graph. This graph represents the connections between data points in a dataset, where each row of the graph corresponds to a data point and the columns represent the indices of its neighbors. The function sorts the graph by the values in each row, arranging the indices of neighbors in ascending order of their distances from the data point, represented by the row. Inputs. Graph. A connectivity graph. This is typically represented as a NumPy array or a SciPy sparse matrix, where each row corresponds to a data point and the columns represent the indices of its neighbors. Outputs. Sorted graph. A sorted connectivity graph, where the indices of neighbors in each row are arranged in ascending order based on their distances from the corresponding data point. Steps. The function iterates through each row of the input graph, For each row, it sorts the indices of neighbors based on the corresponding values in the row, which represent the distances between the data point and its neighbors. The sorted indices are then used to reorder the columns of the graph, resulting in a sorted connectivity graph. Visualization plots. The sorted connectivity graph can be visualized as a heat map, where the rows represent data points and the columns represent their neighbors. The color intensity of each cell can represent the distance between the corresponding data point and its neighbor. The sorted graph can also be visualized as a network diagram, where each node represents a data point and the edges represent the connections between them. The edge thickness or color can be used to represent the distance between the connected data points. Fine-tune parameters. None. Uncertainty methods. The sort graph by row values function does not directly address uncertainty. However, the underlying distance metric used to construct the connectivity graph can have an impact on the uncertainty of the sorted graph. For example, using a metric like Euclidean distance might lead to different results compared to a metric like Manhattan distance. Challenges and fixes. Challenge 1: if the input graph contains duplicate values in a row, the sorting might not be deterministic, meaning the order of neighbors with identical distances might vary across different runs. Sample use case that resulted in challenge 1: when using a distance metric like Manhattan distance, multiple neighbors might have the same distance from a given data point. Fixes to challenge 1: to ensure deterministic sorting, a stable sorting algorithm can be used, which preserves the relative order of elements with identical values. Challenge 2: the performance of the sort graph by row values function can be impacted by the size of the input graph. For large data sets, sorting the graph can be computationally expensive. Sample use case that resulted in challenge 2: sorting a connectivity graph with millions of data points and thousands of neighbors per data point can take a significant amount of time. Fixes to challenge 2: techniques like using a parallel sorting algorithm or exploiting the sparsity of the input graph can be used to improve the performance of the sorting process.